Okay, so my name is David Donis, and this is the physics of a skateboard ollie. So for the topics I'll be talking about today, I'm going to be giving a brief history of skateboarding, as well as the advances that have been made to the art of skateboarding. And most importantly, I'll be talking about an ollie and what that is. And for those of you that have never seen it, I'll show a brief clip. And of course, I'll be talking about the physics related to an ollie. And this includes the coefficient of friction and how much force is required to propel a skateboard along different surfaces depending on the wheels. I'll be showing a force diagram and how the forces are distributed when the ollie is being performed. And I'll be talking about Newton's second law, which relates force with mass and acceleration. And of course, I'll be talking about potential and kinetic energy and the relationship amongst themselves and how this is transmitted when performing an ollie. So the brief history of skateboarding begins in 1950 when California surfers looked for a way to bring surfing to the streets. And typically this was constructed by attaching roller skate wheels to just regular wooden boards. And they created this in a way to kind of compensate for the times when surfing was not possible and where the tides were not adequate for surfing. So this brought surfing to the streets. In 1972, urethane wheel is created by Frank Nasworthy, and this is a big deal because urethane wheels are still being used to this day, so you can find that on most skateboards. And in 1978, Alan Ollie Gelfland invents the ollie, a revolutionary new trick which completely changed skateboarding and kind of brought back that interest in it, and it began the whole frenzy of learning tricks, and really it just became a lifestyle after that. So here's a brief video of an ollie for those of you that have never seen one. It's pretty brief. Okay. So we can see, based on these first three frames, the progression of an ollie. And typically what we see is that in an ollie there has to be some sort of diagonal upward motion. So the first frame shows red arrows, which represent the force exerted by the rider, and the blue arrows represent the normal force of the ground pushing back up against that force being created. The little black arrow represents gravity, and we see how the distribution of the force of the rider is actually concentrated in the back, and this will provide that pop where the normal force is going to transfer that energy upwards, and one side of the board is going to lift up at an angle and create that kind of vertical upward force, or that pop in an ollie. So in these next four frames we see that there is no normal force anymore because it is off the ground, but we do see that the rider is kind of leveling out the board little by little and guiding the board back to its horizontal position so that the rider won't land the same way that he propelled off the ground. And we see in the last frame that the red arrows are distributing the force exerted by the rider, while the blue arrows counter that because he has now made contact with the ground once again. And the black arrow is present throughout all the 7 frames, representing gravity. First, the next topic, Newton's second law. If a net external force acts on an object, the object accelerates. The net external force is equal to the product of the object's mass and the object's acceleration. So we see that in the equation, the force is dependent on the mass times the acceleration, the mass being in kilograms, acceleration in meters per second squared. And we know, of course, that if we don't exert any force onto a skateboard, it won't move. So we need to have some sort of force present in order to create any kind of movement. So we can see that if we have a constant acceleration, in this case as an example 4.0 meters per second squared, and we're given different scenarios, the first being a rider that weighs 70 kilograms, we're going to multiply that by the acceleration to get 280 newtons. If we have someone who's heavier, say 120 kilograms, the force needed to propel that person at the same acceleration is 200 newtons greater. So obviously we see that the relationship between mass and acceleration determines the force needed to propel someone at a given acceleration. And of course we also relate this to the coefficient of friction, which is the amount of force one object must overcome to move over another. The equation for the force of rolling friction is the force needed is equal to the coefficient of friction times the normal force. So if we have a normal force, we want a small coefficient of friction to minimize the outcome. In this case, a smaller force needed. And typically that's what we're looking for, a small coefficient of friction. So here I have a graph or a table that shows that the different hardness of the wheels determines the coefficient of friction. In this case, what I was able to find was that the surface is polished steel, and we see that different hardnesses, typically greater ones, produce a higher coefficient of friction. So there needs to be some sort of balance, typically a little bit softer but not too soft, otherwise the coefficient of friction is going to be greater than what's needed and to effectively propel a skateboard forward. For potential energy, this is the energy difference between the energy of an object in a given position and its energy at a reference point. So this relates to the transfer of energy as a result of the transition to a resting phase to a motion. And the equation for the potential energy is mass in kilograms, gravity in meters per second squared, and height in meters. The kinetic energy is the energy of motion. So we have the equation, the kinetic energy is 1/2 mass in kilograms, velocity in meters per second, and that is squared. So for the units of both potential and kinetic energy, we have joules, which is a newton times a meter. And the kinetic energy can relate to the free fall after achieving the highest point of an ollie. So as an example, suppose we have a skateboarder whose mass with his skateboard is 198 pounds. He ollies off a tall ledge that is 12.5 meters tall and onto the concrete sidewalk below in order to attempt a world record. We need to calculate the kinetic energy of the skateboarder just before impact, and we're given that gravity is 9.8067 meters per second squared, and we're told to neglect air resistance. So to understand this problem, we need to understand the relationship between the initial potential energy and the final kinetic energy. And in this case, they're actually equal. So we're going to use the potential energy formula, which is mass in kilograms times gravity meters per second squared times the height in meters. So we have gravity already in meters per second squared, but our mass was given in pounds. So we need to convert that by dividing using a conversion factor to obtain 89.8 kilograms, and height is already in meters. So after multiplying these three together, we get an answer of 1.10 times 10 to the fourth joules, and that is the amount of kinetic energy that is being achieved right before impact. So that's the potential energy being transferred into final kinetic energy. So all in all, the skateboard ollie relates topics such as force, how much force is needed to propel the actual skateboard, and gravity, of course, which will result in the skateboarder descending after providing that pop of the skateboard. Potential and kinetic energy, and how these concepts relate to the ollie, and the transfer of energies, as well as friction, which also matters because there's different surfaces that a skateboarder can, travel against, and how some will provide more resistance than others. And we have weight, which also affects how much force the rider needs to exert when skateboarding. And we see now that there's been so many advances to skateboarding that's made the ride a lot smoother, and the possibility for expression and doing all sorts of tricks remains limitless. And interestingly, skateboarding is now an Olympic sport, and you'll see it in the 2020 Summer Games in Tokyo. So that's pretty interesting. These are my sources, and that's it. Thank you.